and welcome to GeoTalks. My name is Ben Follett and I am a Principal Engineering Geologist for Engineering Consultants WSP. I'm based in Perth, Western Australia. I've pre-recorded this GeoTalk given the time difference between Perth and the Eastern US, but if you have any questions, I'll be happy to answer them in the next day or two. This GeoTalk presents the use of Global Mapper for modelling of ground settlement from construction activities. But really, it demonstrates just how versatile Global Mapper is when the separate tools are combined into a workflow. In construction, excavation of open trenches below the water table often require well pointing. This is where a line of wells are installed along the edge of a trench and water is pumped up. This pumping creates a cone of depression where the water table is lowered to provide the dry trench, but the cone extends well beyond the trench edge, and the process of dewatering can cause settlement of the surface as soil particles readjust due to the change from the saturated to unsaturated condition. This in turn can cause settlement of overlying structures that sit above the cone of depression. So before dewatering operations can go ahead, it is necessary to understand the effects on the surrounding structures so that operations can be modified to minimize those effects. Often this is done through the formal planning or consenting process. The shape of the cone of depression is a function of three variables: soil permeability, depth to groundwater, the depth of the well or trench. And there's a simplified formula for calculating the width of the cone, which is useful as a first pass assessment. A further formula can give us requires another variable, the soil strength, and from this the amount of settlement can be estimated. Whilst there are more detailed theoretical models that exist, the above process, as detailed in Serial Guide R113, is used as a first pass, a screening test if you like, and is generally found to be conservative, i.e. it overestimates the settlement effects. This means it is therefore safe from the point of view of assessing the effects of structures. If we find that settlement is predicted via this model, we can go back to individual sites and do a more detailed analysis to get a more realistic settlement using more complex and sophisticated models. That's all I'll say about the theoretical background. For the simplicity, in this example here, I work with a pipeline that has 4 parts, each with different variables to represent the different range of pipe depths and soil conditions that might occur as a pipeline route passes through variable soils, variable topography, and variable groundwater depth. So in the south, we have a 6-meter deep pipe in sand with groundwater at 2 meters, and the parameters change all the way through the length of the pipe up to the north, which is 3 meters deep in sand with groundwater at 1 meter. So remember, what we're interested in is understanding the effects our dewatering has on nearby structures. And those effects vary as a function of our 4 variables: the trench depth, the groundwater level, the soil type, and the distance from the well point. This is a cross-section of the cone of depression. I can simplify this curve into 4 sections and use the attribute calculator function to calculate the settlement and distance of each section and for each pipe segment. In this case, I'm going to calculate my 0mm settlement drawdown, my 18% settlement drawdown, my 39% drawdown, my 57% and my 100% drawdown. So we are juggling a lot of variables here and calculating the drawdown at 5 points on either side of each segment, noting that drawdown is directly proportional to the settlement, and so by understanding drawdown we can calculate the settlement. Here I have my pipe segments with those variables that I mentioned earlier: permeability, groundwater depth, well depth or trench depth, and this is a C factor that will allow me to calculate the cone width. So the cone width will be my 0% drawdown contour. Following on from that, I can use the attribute calculator to calculate those other settlement contours. First of all, I'm going to generate the width, so that's the radius for each of those variables, and next I'm going to then derive the millimeters of settlement at each of those 4 or 5 points. So now, having calculated the settlement for each of my 5 drawdown increments and for each pipe segment, I'm sure you can see the next step coming. I'm going to use a buffer function to create a single buffer for each of my radiuses using the buffer by attribute function. I'm going to repeat that for each of my radii and put each one on a separate layer. Here are the buffers. I've added styles and put each one on its own layer. The neat thing is that the buffers have inherited the attributes of the parent object. So here you can see I have my 100% radius buffer, that's my 0mm settlement contour, which runs along here, but it's inherited the attributes from the center line from which it was derived, the center line being my pipe length. So it's picked up the permeability, the groundwater depth, the well depth or trench depth, etc. The next step might seem surprising or unnecessary, but it comes in handy later. You see how the buffer ends clash around here. This is not realistic because other overlapping well points do not cause double the settlement where they overlap. So I'm going to manually clean up these, as it will make the settlement slopes, which I generate later, look very ugly. It's not entirely necessary to manually tidy them up. I could grid them and combine the grids, but when I do that, I find I still get steps appearing in my settlement slopes. So this manual operation is just a relatively quick way to fix that to get a nice looking output. The quickest way I've found to do this is to use the area to points tool. This converts the buffer areas into points. This is found by right-clicking an area and selecting the Create Points features spaced along selected features under your advanced feature creation options. Here I'm using 1 or 2 meter spacing points. Once again, the points generated have inherited the attributes of the parent line. I can use the Lasso Tool to manually delete one of the overlapping pair of points. To pick which one, I can interrogate the points to see which has the greatest settlement. And I'm going to leave the greatest settlement and I'm going to delete the lesser of the two. I repeat that for each segment and for each layer. Here's my finished product. I've maintained layering as a per percentage drawdown, as we had done previously. And I've now got a point cloud that I can grid. Before I do that, I assign what attribute is elevation for each of my 5 layers. I'm also going to tell it that I'm working in millimeters here. As an aside, the settlement shown is negative millimeters. I can then use the grid function to make a grid. To set the elevation, I right click on each individual layer, select elevations, and then select the attribute that I want to use as my elevation for that particular layer. I'm also going to include the millimeters attribute here so that we know what units we're working in. Now I'm going to create my grid. To do this, I'm first going to create the extent of my grid by selecting the area, then create grid using the create grid tools. It's asking me what layers I want to use, which are my points and my final extent buffer. And I can define the spacing I want to use, which in this case I can go for a very fine spacing because we haven't got a huge area. And I click on grid bounds to crop to my selected area feature. I've not mentioned this before, but there's a second construction effect that can cause additional settlement when excavating a trench. And this occurs as the trench walls move laterally into the trench as excavation proceeds. The effect is localized, but I can model it in exactly the same way using a separate equation. I won't go through the parameters now, but they're very similar to the ones that we used previously, but the curves are different and the effect is much smaller in lateral extent, but can be a lot larger in terms of total settlement localized around the trench edge. Here is my model for the settlement that's induced by the lateral wall movement as excavation proceeds. You can see that it's far more localized than dewatering induced settlement, but its effect does combine with the dewatering induced effect to create one overall combined effect. And as we get very close to the trench edge, the two effects as they're superimposed can be quite significant. So what I want to do here now then is to combine the two grids, my settlement induced from dewatering and this settlement I'm showing here, the wall movement grid, into one complete combined elevation grid. So to create my combined elevation grid, I turn on the two layers I want to combine, go to the Combine Compare tool, the operation I want to do in this instance is addition, so I'm adding two negative numbers. These are the two layers that it's going to add to combine, and I need to tell it that my vertical units I'm working on is in meters. Those defaults are set at about 0.5 meter spacing, which is the native spacing of my grid, so I shouldn't lose any resolution by doing this operation. There's my combined grid. We can tell that it combined correctly because the maximum settlement now showing is double or is the sum of the two maximums from those individual grids. So that must have meant that I've calculated it correctly. I can use the path profile tool to look at it another way by cutting across a line across like that, we can see our original settlement contours and now a much steeper profile in the immediate vicinity of the trench, and that represents the steeper contours associated with settlement induced by lateral wall movement as the excavation proceeds. Now I've got my final grid, I can contour it to see what the effects are on the surrounding structures. There are two types of settlement that I'm interested in. Total settlement, that is a total vertical movement from pre-construction to post-construction, and differential settlement, which is the slope of the settlements. So buildings are particularly prone to or susceptible to differential settlement. So if the front half of the building settles more than the back half, it doesn't matter necessarily how much the entire building settles as a whole unit, total settlement, but that stretching which occurs when a slope occurs because the front settles more than the back can be particularly damaging. So I'm going to want to look at both total and differential settlement by looking at my settlement as contours in millimeters and settlement as slope. And Global Mapper gives us those tools. Let's tackle the slope settlement first. I've set up a custom shader for a 1 in 500 slope. So what we find in engineering generally is that 1 in 500 slope angles are typically an amount which buildings can tolerate with minimal effects, or general typical buildings can tolerate. Anything more than that, we start to see visual effects of those settlements as the building stretches. So I've created a shader which only shows the portion which is greater than 1 in 500, which is the equivalent of 0.11460 degrees, rather precise. So by putting a bit of transparency on there, let's zoom in. We can see where it's predicting the 1 in 500 slope effects. And the front yard of this person here is affected, and that's close enough to be of some interest to me. Elsewhere down the street, the effects are further from properties, and as the pipe gets lower or the permeability gets less, the effects get further and further from properties. Of course, if I had a really long pipeline that was going many kilometers, I don't want to look at each individual property individually and write it down. I want to try and somehow get the GIS to just extract which properties are affected and which aren't. I can't do this really from a grid directly, even one that's shown in as a slope, because it effectively sort of works a bit like a raster. So in order to generate something which I can query against another layer, another vector layer, I need to vectorize this 1 in 500 plot. Global Mapper gives us a tool for doing that. We need to first export it as a float file. So that's under your options here, a float grid file. And it gives me some options here, and one of them is to export slope values instead of elevations. And that's what I want to export. So I can create a new kind of grid that I can contour. I've exported the float file and I've brought it back in, and this is what it looks like. What it's reporting to be showing here is meters, but that's not the case. It's actually showing degrees, because if you remember, we exported it only as a degree file. Because I've got it in this format, I can contour it, and I can be it gives me the ability to contour in degrees. So just using my normal contour tool, create contours, I can create contours at a specified interval, which in my case is going to be my 0.114460. It thinks it's meters, we know it's not. We only want it to generate contours at that specified height. You can see it's brought through the 0.5 meter grid spacing, so I've not lost any resolution. I'll let it smooth the lines. I don't think I need any bounds. And there you can see the 1 in 500 slope has now been contoured. If you don't believe me, I can show you my elevation grid back again, and you can see it lines up pretty well. Now that I've got that as a vector, I can query it against other vector values, which might be an underlying cadastral showing property boundaries or house boundaries, to pick out which house boundaries or which building boundaries are located within the 1 in 500 slope. And this is one of the powerful things about Global Mapper, certainly I find really useful, is that when it creates a grid, it can create a grid for elevation, for slope angle, and for aspect. And you can export each of those, turn them into vectors, and query them against other vectors in your plan. So this slope angle here, we're obviously looking at really small slope angles of less than 1 degree, but on a district-wide scale, the same function can be used to extract vectors for breaks of slope, say for gully crests on an entire watershed. So it's a really, really versatile tool. So now that I've identified this property might be at risk from my development, but most of the other properties along the alignment look fine, I can do a more detailed analysis of this one property in 2D using some other tools, some specialist geotechnical software, to look at this one case individually. What Global Map has allowed me to do then is save me analysing every effect along in detail, and instead allow me to focus my time and effort on the one property that I really need to. So then, a summary of the workflow. We started with our inputs of our soil type, groundwater depth, and trench variables. We included those as attributes along the lines. We use attribute calculator to calculate the drawdown and settlement at 5 points of a generalized curve. Then we use the buffer function to make contours of our drawdown at those 5 points along that curve. We use the area to point tool to create a point cloud, because a point cloud was easier to tidy up than to tidy up vertices. We repeated it for the second equation, and I rather skipped over that one, but it was essentially a repeat of the first operation. That gave us a point cloud of our settlement due to lateral wall movement. We gridded both point clouds, and then we used the combined grid function using the addition option. We viewed those grids as slopes using a custom shader, and then we exported the combined grid as a float file type, having selected export slopes, and that exported the slopes or the angles of each of those cells in the grid. We brought that back in to Global Mapper so that we could contour the slopes, and we contoured the values of the slope to create a vector of the 1 in 500 slope angle, and that was our final contour. And then, because it was vectorized, I could query that 1 in 500 slope vector, any other vector layer, if I'd have had them in my data set or if I'd have needed to. Well, that's all from me. Thank you for your interest. It's been a pleasure, and I'll answer any questions through the app in the next day or so.